Okay. So it seems like the errors in the system model A, the matrix MFS, are much higher than the noise in the data collected. So we've got to either, I say three ways to go. One of them is just go back to using a regularization parameter, and I really don't want to do that. It's very hard in the clinic to have a technologist choose a regularization parameter. There's no way to know what the regularization parameter is ahead of time. It's just not a good option. Okay. We could try to find a bound on the error of A, AX minus B, or we could just reconstruct each coil's image independently, and then use joint sparsity, and then combine the reconstructions once we have the reconstruction of each channel. The issue with that is that we don't use the sensitivity maps in the individual reconstructions. So we either have to, it's like we're losing the power of the acceleration from sensitivity encoding. So we either have to try to find a way to incorporate the sensitivity maps into a joint sparsity reconstruction, or flounder and hope we figure something out. That's what we're doing today. All right. So my one idea for finding a reasonable bound on the sensitivity maps is to call Pisco twice. I think everything we did yesterday was junk. Everything was junk. It was just so silly. Oy, oy, oy. In fact, you know what I'm going to do? Just going to revert. Okay. So Pisco has this dimension that is tau. This parameter that's tau. Let's expose that parameter. Okay. So now we could call Pisco twice with two values of tau. Tau is half the window size. Okay. So if we thought T3 was fine before, what is it now with a window size of 4? Oh, goodness. Go back to this. Tau. Didn't I just expose it? Oh. What's the difference in these sensitivity maps? Okay. This is with a tau of 3. This is with a tau of 4. 3, 4, 3, 4, 3, 4. Okay, and so this tells us something about the sensitivity maps. These are the sensitivity maps that you would estimate if you assumed that they could linear combine into complex exponentials of frequencies related to the integers -3 to 3, and this -4 to 4. So this is how well the sensitivity maps combine into a slightly higher complex exponential of a slightly higher frequency. What is the difference between, let me look at the supports, by the way. Huh, that's interesting. Okay, unsurprising, the supports are different. That's fine. Now what's the norm? S maps minus S maps 2, 93 divided by num-L S maps. 1 times 10 to the -4. What was the error in AX minus B? Two times that, square root of that, 1 times 10 to the -3. Huh. That's the standard deviation of the error, I think. Right. No. Okay. So that's a times 10 to the -4, and we had a times 10 to the -4 over here for the difference in the sensitivity maps. Was that coincidence? By the way, it's not what we want, because what's the variance here? Right. This again is weird because, no, never mind. See, this here is a metric of how bad the system matrix MFS is. Pretty tough. Pretty tough. So we need, but that's a lower bound on the error, right? What if we looked at, yeah, this should have been norm squared. Let's do that. Point 0.01. That's 0.5. The difference between these two is about 0.4, 0.5. The difference in the norm of those matrices. Is that just an error? Is that the knee? How do I not easily? I use the knee like, seriously? We don't have any knee in here? That's just silly. Here's a brain. Okay, we'll use 6. Ooh, 4.5. Much too high. Okay, so that was just coincidence. 42. Getting worse. Oh. Oops. I think I mean, so I was like, I don't know what I was doing. Five. That's with the brain data. Is this just noise? Like, perhaps instead of going up a window size, we should go down. Okay. What about just taking the norm squared of the difference and divided by the number of elements? Take the square root of that. 0.2. Let's go the other way again, where we're going to go up. .15. These are reasonable numbers. The other one was 0.2, right? So not drastically different. Okay. This W size is like 2 times tau plus 1. Can Pisco work if tau is 2 elements? Third one. Yeah. My goodness. Here's where it would have been. If you could have done tau 1, tau 2 here. That's at least one place. So he's assuming it's a square. By he, I mean the guy that wrote Pisco, who's Rodrigo Lobos. Okay? This is not good. It's just for a minute. Just for a minute. That's nobody. Well, maybe we should just do it out here. CS error bound is equal to norm. What the heck was it? What's that error bound? .15. And what is it for? Data case 9? 0.12. Okay. If that's it, then I want this without the square root. Are these reasonable numbers? I forgot. I was thinking of the radius, but this is actually just the like the error in the sensitivity maps. Okay. How is the Frobenius norm related to the spectral norm? Okay, the Frobenius norm is the sum of the squares of all the singular values, and the spectral norm is the largest singular value. Okay. So is the Frobenius norm the Schatten 2 norm? Yep, the Schatten 2 norm is the Frobenius norm. Okay. is this value? Times 10 to the negative 7. This is times 10 to the negative 6. Oh, this should have been CS error bound. 0.01. Now, hold up. This is 0.01, and this is tiny. That is on the order of the noise. What on earth is going on? Oh, because that's variance, not standard deviation. I don't think this is going to be good. But we'll verify. Okay. So this is equal to this, which is equal to this. So the indicator of that is a projection onto the ball of this radius. This is going to be an infeasible problem, almost certainly. Okay. Well. Oh. Oh, shoot. Okay. This is almost certainly not going to work. And the question is, does it not work because the threshold's bad, or does it not work because there's a bug in the code? Okay, so it didn't work. What was that radius? Too high. 51. Hmm. This is way too high to get a good result out. So the indication is that that's not a reasonable error bound. What do we need there? What value do we need there? If we want radius to be 0.1, .01 divided by NV. something times 10 to the negative 8. What's the noise variance? Times 10 negative 11. Times 10 negative 6. So if we put the standard deviation in for the variance, it works in this case. Great. Just great. Ah. Do I have an apply M? What is the usage of power iteration? Not enough input arguments. Oh. X0 must be non-zero. Logical indices contain a true value outside the array bounds. Oh, right. And that's enough. Just wanted the norm of M. We have the norm A. But what about the norm of MFS? $255. 1 divided by 255. 0.003. But that doesn't tell us whether S is correct or not. That just tells us the norm of MFS. Okay. So now we've replaced, inside this code, we've replaced SMAPs with SMAPs2. What's the norm now? About the same. 255.9551 minus 255.9441, 0.01. If we square those things, if we square root that, so this is the difference in the largest singular values, 0.01. Okay. So there is at least a combination of numbers that will get us the value we want. ACR. The problem's feasible. That's a good image. And I suspect that was a total hack. It just happened to work out for the first data. And now we're going to see if it happens to work out for the second data. If it does, if it happens to work out for the third data, then maybe it's not happening to work out. Maybe there's a reason. Right now, there's really no reason to think that's true. There's this parts of the objective. Oh, Vista. What? Was it infeasible? Infeasible. Why was it infeasible? What just happened there? In order for this to be 0.2, 0.2 squared divided by NB. Let's make it 0.1. Did I forget to change? Why is it still showing me? Oh, it is a brain. Okay. Okay. Oh. Okay. 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 So this didn't work. Didn't work. And that's not shocking. What does that leave us with? We have a metric for the error of the norm, or for the error in the sensitivity maps. You know how much the sensitivity maps might differ? And that doesn't seem immediately related to MFS, the norm of MFS X minus B. Pretty tough. I've seen his name. For sparsity regularization, we employ Stein's unbiased risk estimate criterion to select the wavelet regularization parameter and local standard deviation of reconstructions to select the TV regularization parameter. Stein's unbiased risk estimator, SURE, produces online estimates of the expected mean squared error of a reconstruction model. Accelerated MR imaging using compressive sensing with no free parameters. I don't recognize any of those names, but if they solve my problem, I most certainly will remember them. This problem can be solved with Vista. This is the gradient descent. This is a gradient descent of just this term. This is going to be soft thresholding. Sure. Sure. The coil sensitivities are normalized by the sum of squares of all the individual coil sensitivities. I don't, that's a point. So in this problem, yeah, this is MFS, right? Well, any solution to this is also the solution to S hat X, S hat Y, where S hat is equal to SK and Y is equal to X over K. Or rather, yeah, right. So these two have the same solution. There's a scaling ambiguity. And if we're going to be measuring the difference in the sensitivity maps, then maybe we should normalize them. We, of course, normalized the K-space data. possible Pisco's already normalizing them. Some coil sensitivities are normalized by the sum of squares of all the individual coil sensitivities. Do they mean all the individual elements of the coil sensitivities? I can scale all the S maps. How do I want to scale them? I want to scale them so that the sum of the square root. This also means how to normalize sensitivity maps in MRI. Normalization is crucial for accurate image reconstruction, particularly in parallel imaging techniques like SENS and GRAPPA. Yeah, but how do you normalize these things? Okay. SI hat is equal to 1 over the square root where SJ are the normalized sensitivity maps. How do you normalize them? The norm of the eigenvectors at each location are normalized to 1, and one arbitrary chosen channel is referenced with 0 phase. Okay, AI, come through for me. How can you normalize sensitivity maps for parallel MRI reconstruction? Okay, this is reasonable. So you take the sensitivity map and you divide by the square root of the sum of the squares of the sensitivity maps. Okay. Here's another one that's reasonable. So that maximum magnitude of the sensitivity is 1. I like this one better. Normalized sensitivity maps. Square root the sum the magnitude squared out is equal to S maps divided by square root of the sum. This is in the third dimension. Think that'll work? Let's see if they're different. So the magnitude goes from 0 to 0.88. Magnitude goes from 0 to 0.88. It looks like they are already, the mean is 2.788. 2.788, then sensitivity maps are already being normalized. Okay. And they're being normalized this way. That's interesting. We're definitely going to copyright that. I mean, that is valuable. Okay. So then that wasn't the issue, so we're going back to the paper. Unlike FISTA, we do not. FISTA is an optimization algorithm. So they say, unlike FISTA, we do not use a fixed threshold that will need to be tuned empirically for any clinical application, but make the threshold selection dependent on the current guess solution. Well, then, are you guaranteed to converge? So here it's like they are changing the regularization parameter in each iteration. And that means you're not solving the same optimization problem in each iteration, and that means you're not guaranteed to converge. In implementing the SPIRiT method, we have used the standard practice of estimating the noise standard deviation as 1.4286 times the median absolute deviation of the finest scale wavelet coefficients. Uh-huh. Why 1.4286? That looks like a threshold to me. We have 3 data sets. Okay. Optimization of regularization parameters. Of the wavelet coefficients of what? I don't know, man. I know this paper. I actually implemented this and it didn't work for me. Could be that I had a bug in my implementation, but it seemed like a pretty simple technique. The improved Stein unbiased risk estimator is developed to automatically tune the shape parameter to be effective for a variety of noise levels. It's not difficult to found. Smooth L0 norm, okay? Okay, and then they stopped showing me this paper. Is this the one we already looked at? Lawrence Wald. Okay. Oh, this is based on Tikhonov regularization, which is not compressed sensing. So, shoot. The local standard deviation estimates, that's like, reminds me of bilateral filtering. S-curve, I think people have tried to look for the knee in the Pareto optimal curve, and I've seen that not work well. AI is recommending the Varela paper, Varela Matatal, I don't know, Matatal. So they're doing it with Lorax, which has a different data consistency term. Yeah, so they're getting away with it. I'm about to just go to joint sparsity. How long have we been at this? An hour. Okay. I don't have anything better. So joint sparsity it is. The first step to joint sparsity is making this work for just a single coil. So I think S maps now is going to be an optional parameter. Okay. One. Great. So that still works. Let's get rid of a whole bunch of these displays that I don't want to see for a while. So what's going on here? So we used to take the variance of the noise of the reconstructed image after combining all the coil images, but that of course is not correct. What we want is the variance for the noise values for each coil. So we're going to use that value there. That's my first appointment today. Okay. I'm going to go back to checking it out. Git status. Let's revert again. Git checkout MRI recon spirit reg.m. This code, the normalized sensitivity maps, I'm actually going to move into the work library, and that's just to remind myself how to normalize sensitivity maps. I don't know what this DS store file is. I know it's a Apple system file. I wonder what it does. Whoa, a whole bunch of differences here. Added some spaces. Gotta keep that. Okay. I spent a whole bunch of time writing notes in Git, and I never look at them. I should have said should be equivalent. Okay. And now we've added as long as we're here, we've added normalized sensitivity maps to the repository. Coil compression doesn't work. And this we don't need to change. Okay. Great. I want to know what happens if the sensitivity maps if just one coil is passed in. So an optional parameter doesn't have what? Oh, I checked it out after. Okay. So we're back to having S maps here. These are not in alphabetical order. Okay. If an image and coils is greater than 1, error must supply S maps with multiple when with parallel with multiple coils and otherwise S maps is equal to 1's S image. Okay. You wouldn't do SPIRiT regularization with just one image, of course. Cannot perform SPIRiT reg with only one coil. So does this work now with one coil? Let's find out. The answer is no. It's clearly going to be broken, but let's find out why. This is the first reason. You're kidding. It's running? Okay. That's the compressed sensing result. Okay, so it ran, great. And then we got cannot perform spirit reg with only one coil. Great. This works better than I expected. I wish I could fold one of these things. Can I? No, that's just one function. Okay. Okay. Apply MFS image 0. So if n coils is equal to 1, image 0 would just be the zero field reconstruction. So apply M K data. Oh, K data is also already zero filled. FFT shift 2, FFT 2, IFT shift 2, K data. Think that's right? Let's find out. Right. Yeah, right. Okay. Silly. Okay. These go here, of course. Nice. A slightly faster way to get an initial result. We don't have to call it iterative reconstruction algorithm. What I want to know now is what is the norm to apply MFS to image 0 minus B. Numerical precision. Right. That's what I expected. And so now let's see if we did all this stuff right. Okay. Yeah, we didn't. Oh. It's times 10 to the minus 31. It's 3 times 10 to the minus 31. Noise variance is 3 times 10 to the negative 11. So now when we're here, this should be totally feasible. So noise variance is times 10 to the negative 11. We're going to multiply that times 10 to the 4, and multiply that by 2. So that should be 3 times 10 to the negative 7, and it is, which is much higher than times 10 to the negative 16, which is numerical precision. So if this is GDC, and this is the bound, right? So what's the projection? What's the radius of the ball that we're projecting onto? 8 times 10 to the negative 4. So for this single coil, that is a very feasible problem. Here, S maps is just ones, right? But the norm didn't change much. I guess the norm is related to the discrete Fourier transform. That'd be my guess. Yeah, they're all ones. The taus are reasonable? That's encouraging to me if the line search is choosing reasonable taus. Okay. This is what compressed sensing is getting us. Okay. So now we're going to go back and supply the sensitivity maps. We're going to use all the data from all the coils. And if compressed sensing is true, what on earth am I doing? Okay, so we have this working with a single coil now. At least the compressed sensing part. We should be able to do compressed sensing with support. Support is a single coil thing as well. I don't want to do that. I just want to work on compressed sensing today. I have to leave in a little over an hour. Okay. So now with compressed sensing, what I'm suggesting we're going to do, what we're going to do is check this in before I mess this up. Okay. What I'm suggesting we're going to do is this. So this is the L21 norm. It's group sparsity. We're gonna assume that the sparsity patterns in the wavelet domains for all the individual images are going to be the same. That's what group sparsity does. And this is actually equivalent to this. So the data constraint is going to be the same. That's shocking to me. That's interesting. Okay. Oh. No, this won't work. Why not? Okay, I want to do data consist. I want to do group sparsity. Yeah, Okay, this can't be this hard. Okay, so now here's where I want to try to use the sensitivity maps. We've got Y. This is the best I got. There's no multiplying by 1.4286. There's no looking at the wavelet coefficients of the highest frequencies. You just look at the noise, which you can measure with MRI. This is actually, if this bloody works, this would actually be a parameter-free reconstruction. Okay, so it is a parameter-free reconstruction, but there's no reason to think that this will work well. And we're about to find out. Okay. GCS. I need the L2 norm, L21 norm. L21 is not in here. Work lib norm. Norm L2 L1. Okay, open norm L2 L1. WS are going to be the weights, I bet they are. Candes wrote a paper called iterative rethresholding, but I found that that had a hidden parameter as well. We're going to go with this. Let's see how well this works. Now I need the proximal operator of L2L1. Prox L2L1. Okay. So here N is going to be M by N coils, but instead of the sensitivity maps, those are the images. N is going to be the images here. And actually, it's going to be the wavelet transforms of the images. Okay. So I think that's ready to rock. So the difference is the data consistency term here, instead of being MFS, is just MFY now. Okay. Where is ADC? I don't ever create an ADC. But I do have GDC. Okay. So if we're using compressed sensing, at this point we already have GDC, so where did that come from? Oh, right. We just, okay. Pretty tough. Okay. Apply A should be concat psi MF. MF. Huh. MF. So now psi, we're requiring that psi operate independently on the coil dimension. Okay, nice. This should be n image times n coils. And it is. Images of all, coils of all images. Where are we? Noise var. Noise var is not equal to 0. I just added a line to the code, so that messed it all up. Okay. Compressed sensing problems infeasible. Why? Because I have MFS there. I haven't checked an adjoint in a while. Apply F. Apply F doesn't exist. Actually, let's do that, because it should work on three-dimensional data. And it does, okay? Okay. How many places do we have FFT to H? Two, apparently. Lots of them passed. Concat. Check adjoint. Hmm? Yeah, okay. So this should be SK data. Arrays have incompatible sizes for this operation. What on earth is happening? Oh, Lord. So in here is size 256 by 256 by 8. What is psi in? 250. Ooh. Wow, okay. Our own Debouchet transform didn't do what I wanted. It doesn't satisfy a requirement. We call this psi default. Oh. If we call this default psi out, I'm not going to do it. I think I can make this a little more efficient. Makes the code bounce back and forth between, the code up here will be dependent on code way down there. Let's just keep it this way, certainly for now. Okay. $293. Okay. 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 We're back to this. Okay. We finally got past the place where a problem was infeasible. Right. So now we're solving that problem that we were going to solve. But now, so there's this post-processing section. If CS is equal to true, then we're going to do something. Else, we're going to do this. It's a complicated code because we're trying to have it do so much stuff. Here, we're going to set this equal to image. set image not equal to recon roamer. Now we need an applied VMF. I think we also have a reshape here. Oh, right. Well, okay, so now I want to do checks. So I can just make this NK data. Why? Oh, okay. Right. Right. Actually, this doesn't need a reshape, does it? Okay. MFS, MFS. That doesn't seem right. Like in MFS, we have a P that's optional based on the noise variance. We're gonna have to do the same thing for MF. But if we do that, then we just do this post-processing if CS is true, and then otherwise, and then whatever happens, we do this after. So I need to change this else, put the end there and detab these. What does the recon number do? That's not good. Or is it? Is that good? So that's a Romer recon. Ah. Initial guess must be a column vector of length 256. What? Oh, this should just be apply S. Okay. So let's do what I said a second ago. Or is it the other way around? It's clearly not. Okay, so I think I was wrong. Do I have an apply S? No. Only have apply FS. Putting the P in there. No, I'm not. Okay. Does stuff still work? So here, I guess I could just say instead, in the post-processing part, if size of image 3 is greater than 1, it'll just, okay, so here we've got image 0, and for right now, there's no support included. There's no non-rectangular field of view. So image is equal to reshape image S image. It's working. I mean, it's operating, it's computing stuff. Tau seems reasonable. It's not going bonkers. It's slow. Much slower than it was before. Guess that's because of the L2-1 norm and its proximal operator. Okay. Whose image? Bigger. Show image cube, absolute image. This is what the problem is reconstructing. Okay? Now this looks bad, but I don't know. Let's see. Why does that fail? Okay. I need to save an image so I could just call that line of code without having to go through all this again. But, okay, and it's not going to let me scroll up and see what's going on. Oh, it's because I need VS. What just happened? Oh, I got there. Okay. Nope. bias is not in do checks. Okay. Gonna have to wait for compressed sensing again. A lot of this is probably just iterating over the coils in the wavelet transform. So if I just make the wavelet transform operate on the coil dimension, like vectorize across the coil dimension, then this should be just fine. And that shouldn't be too hard to do. But if I'm going to start messing with the wavelet transform, I think I should make it based on convolution so that it's the fast wavelet transform. And if I'm going to do that, yeah, so that's going to be a lot of work. So for right now, we'll just put up with the slow code. That's definitely a to-do item, which, we may or may not get to during this series of streaming. It's already 9 o'clock. 2 hours and 30 minutes. I need to leave in half an hour. Initial guess must be why is that the case? Oh, but why has it got to be a column vector of size 256? That's the part I don't understand. Okay. Is that good? Or is that bad? There's a subtle difference between the two, but the difference is noticeable. I don't know if you can see it through the compression artifacts of the stream, but compressed sensing is less noisy. That's what I expected. Like you can maybe see it here. Here, I'll show you. See? Compressed sensing is less noisy. Pretty much what I expected. Is that good? That's zero filled. That's model-based reconstruction. That's going to take a long time to get to the compressed sensing reconstruction the way that we're doing it. You know what? That was model reconstruction, but with a different sampling pattern. What was that? This is zero filled. That looks a whole lot like the compressed sensing reconstruction we just did. This is the model-based reconstruction now. You see all the high frequency noise that we've been trying to get rid of. We definitely got rid of that. We definitely did. I wonder if conjugate gradient is just gradient descent of the conjugate function. That's the compressed sensing reconstruction. That's the zero filled. Ooh, that's a subtle difference. In fact, I don't see a difference. Why would that be? Is the projection wrong? Yes. Oh, wait. Is the proximal operator of GCS wrong? Probably not. Oh, goodness. I think this is a problem because norms in are going to be set to 0. That's the whole point of doing the compressed sensing. The whole point of doing compressed sensing. What we want to do is norms in These are going to be real, so we just do this. We know it's real, so we could just do this. So these are the norms out. Out is equal to in. So open prox L1 complex. Norms in greater than thresh is equal to in norms in greater than thresh divided by norms in times norms out. That might be the same. Except it's definitely not the same when norms in are set to 0. So let's see what happens now. Okay, oh, thresh. All right, anything that's less than the threshold is set to 0, which is what this does. Okay. Megan, norms in, norms in. It's much slower. This group sparsity stuff, the way I've implemented it, is much slower. Oh, of course, you're taking, wavelet transforms of images from multiple coils. Like the optimization variable is much, much larger. So it's going to be much slower. It's larger by a factor of n coils. And that is still basically the same. I mean, it's the same. I really don't like having a deadline. I just want to figure this out. Guess we all have deadlines. Is this doing what I think it does? So this currently doesn't work. So this is just doing a this would be just using the L1 norm rather than the L21 norm. All right, maybe that works. And so maybe we could get rid of this. Pretty tough. Okay. Is there a way to test the proximal operator? One way to do it is to install CVX and then compare the output of the proximal operator, which is a convex optimization problem, to the result of CVX. I can do that. Don't really want to, though. We don't need the absolute value of norms in because norms are always positive and they're real. We also don't need the sign. I haven't thought about weighted norms in a while. I forget too much. but that's okay because this is yeah, okay. That looks right. I was thinking, what if the inputs were complex, but I just take the absolute value to begin with and then compute the norm on the absolute value. I think that was from Numerical Recipes, the book Numerical Recipes. So this code and this code should be the same, except instead of taking the absolute value, I'm taking LP norms. And I think LP norms, if dim is less than 3, yeah, NDIMs. Here I'm doing NDIMs, so we don't need this. Maybe I thought it was better to be explicit, but this is fine. What if 2? What if n is less than... Oh, wait, no, we're over here. What if n is less than 2? P is equal to 2. Yeah, we'll just leave it like that. That's more clear. Prox GCS seems right. Oh, this should be... Oh, no, yeah, right. Yeah, this is right. Okay. Where is that used? Prox GCS. So now we just have to look at the indicator function. Man, this indicator function has given us so much trouble. Indicator function. Is GDC less than the bound? Bound is 2. Whoa. We want this, right? GDC. We want GDC what we want is x minus b squared divided by nb is less than or equal to the noise variance. Okay. This is GDC x equals, okay. GDC needs to be less than or equal to 0.5 times the noise variance times NB. Multiply both square roots, so the radius should be noise var times square root. But that's the... Okay. That's going to be true for all C. That's what we want. To this less than or equal to noise var times numL B of C. And you can, okay, so there is a bug. You can stack these things. So it's MF, let's see, MF, diagonal, MF, Y minus B. But then you want each of those. Okay, so there's definitely a bug. I keep thinking these are reversed, so I'm going to reverse them. It's like the simpler case should go first. This is not, oh, yeah, that's correct. The issue is GCS. No, GDC. That's no longer right. That is the diagonal operation MF, because F applies, if it's vectorized across the coil dimension. Okay. It's GDC indicator that's the issue. If numL n coils is equal to 1, then that's right. Else what? The indicator function needs to operate independently. With a different bound. Yeah, okay. This is one of those cases where I wish I could define a function based on an if statement. Function GDC ind in out is equal to end. And I know that this is conflicting with this. How about this? Ind. Okay. For coil index equal to 1 to n coils, and out equals 0. If norm in index minus b NBC is equal to NB divided by N coils. Coil index minus 1 times NBC plus 1 to coil index times NBC. So this is for coil index 0, this is 1 to NBC. For coil index 2, this is NBC plus 1 to 2 NBC, etc. And we're going to use the Frobenius norm there. Huh. Is greater than NBC times noise bar, then out equals infinity and return. I can parallelize this. Why would I? What is this? Coil index is set inside a nested function. So what? Oh, and okay, let's see if we can Alpine, well, no. Diffs is equal to PSX fun at minus in reshape coil index and coils see I need to do this across what does this do? This is going to be a two-dimensional array, and this is not going to be. Oh, in coils. So this is going to be a one-dimensional array, and so is B. Shoot. Okay, so now this is a two-dimensional array by the number of sample points collected by the number of coils. if LP norms diffs to we're going to take MFX. So that's going to be I think this is 1 squared is greater than MBC times noise var if max of that out is equal to infinity. Else out is equal to 0. Yeah. Okay. This is true here. But now we got this. Okay. Okay, so and then this is correct here. And then we need to do make prox GDC indicator H when n coils is greater than 1. That's where we're leaving off. Oh, it's going to be tough to leave that. Hopefully next stream we'll figure that out. I'll see you guys later.